So next, we move on to discussing Noether's theorem. And here I want to make a correction. So the current that is conserved according to Noether's theorem can have either sign. But the sign convention that I used in last lecture is not convenient for a reason that I'll give in a minute. So I want to correct. I want to use the following convention for my current. So J mu is a conserved current, and I want to have it equal to the derivative of the Lagrangian with respect to del of phi times del phi minus the 4 vector J mu, which arises from the variation of the Lagrangian. And the reason why we choose this sign is that kinetic energy of the field is going to be a positive quantity. So we discussed a couple of examples of Noether's theorem in last lecture. Let me just go over one of them here. So one of the example was that what happens if a field theory is invariant under space-time translation. So let's take the following space-time translation. So I take all of space and move it, translate it by a4 vector minus a mu. So we can call this, say, we can call this mu coordinate x prime of mu. So then it follows that the classical field phi of x changes to phi prime. And if we evaluate phi prime at the numerical value x, then it is related to the old vector, the old field phi, but its argument shifted by x plus a. So note that the difference between the sign here and the sign here. So, how do we make sense of this? Let me just quickly remind you how this is done. So suppose we have a classical field. Along the x-axis is our space, or space-time. And then along the y-axis is our field, phi of x. And now suppose that we introduce a new coordinate, we're going to call x prime. And so this distance is a. A here is a positive number. And this is our new field, phi prime of x. So we see that, suppose we take a value of phi prime, the argument to be 0. Okay, before we do this, we have to specify what our old field is. Suppose this is our old field. So phi prime at its origin is, we see that is equal to phi at a. Now, if I work out what the relationship between x and x prime is, you can see that x prime is equal to x minus a. And therefore, we see that for any arbitrary value of phi prime, f x is equal to phi at x plus a. So thus we see that this relationship is the correct relationship. Now, let's take a to be very small. If a is very small, we can expand phi prime of x as a power series in a. So if a is infinitesimal, the leading term is just phi of x, and then we get a mu del of phi del of x mu. Now, then we see that the change in phi, which is defined by phi prime of x minus phi of x, is given by a mu del phi of del x mu. Here we see that we have actually 4 parameters, a mu. So we are going to have, if our Lagrangian remains invariant or our action remains invariant under these 4 transformations, we're going to have 4 conserved charges. Now, the Lagrangian density is also a scalar. Technically, it's actually a scalar density, but for our purposes, we can consider it to be a scalar. So its change is going to be very similar to the change of the field. So del of L will be given by a mu of the derivative of L with respect to x mu. So now we want to express del of L in terms of divergence of a number of currents. Because we have 4 transformation, it'll be the divergence of 4 currents. So how do we do that? To do that, so we already have a derivative operator, but the derivative operator is acting on something scalar, so we need something where there is an index here, mu, but we see that the index, unfortunately, is over here. So we can change that. We can write delta L to be A of, say, mu, and then we get a delta, a Kronecker delta, with mu upstairs, mu downstairs. So of course, these two things, this thing, of course, gives me this. So, and then we have del L, del of x of mu. And then we can write A of mu times del of x mu. So these are just constant numbers, so they can be brought inside the brackets. And this is going to be our current J mu, but as I said, there's going to be 4 currents because there are 4 transformations. So we also need another index, nu. So the mu index is the current index, and the nu index is the label of which current we are dealing with. Okay, so if I write J mu nu, this thing is the current index and this thing is the current label. So the 4 currents that we are going to find conserved are going to be T mu nu minus delta mu nu times L. And then there's going to be another term which is going to be del L by del mu of phi times del mu of phi. Now let's take an example. Let's take the example where our field theory is a real scalar field theory. So our Lagrangian is given by half of del mu phi minus half of m squared of phi squared. So then you see that if I take delta L and take the derivative with respect to del mu phi, I'm going to get del mu upstairs of phi. So you may be unfamiliar with this sort of derivative. So let me just show you how this is done. So what I'm doing is that I'm taking the derivative with respect to del mu of phi of the first term. Now let me write that as half. And these mu indices are dummy indices. So they're summed over. So let me just use nu here instead of mu because I'm using mu here already. So this is nu, right? So here we have 2 factors. So that means that we have to use the Leibniz rule. And so this is going to be half. And then the first term will be this thing acting on this thing. If I do that, then I get a delta of nu of mu. because if mu and nu doesn't match, then the derivative here and the derivative here will be different, and then the partial derivative will give me 0. So that will be, and then multiplied by del nu phi, the second factor. And then we're going to have another term where the derivative operator will act on the second factor. So I get del of nu of phi, and then I will have del of, and now the point is that here, this guy is upstairs. So how do we do this? What we do is that we bring it downstairs first by using epsilon like an eta tensor. So we write eta nu, say rho, and then we have del of del mu of phi acting on del rho downstairs of phi. So the first term, we are done with it. So we just write, we just do the sum over nu in the first term. Then the derivative becomes del of mu of phi. And the second term is half del nu of phi. This remains. Then we have eta nu of rho. And then we have del of rho mu, delta rho mu. And then if we do the sum in the second term, what we find is we have, so the eta raises this guy, and that becomes rho, but there's a rho here, and that rho will, will be summed over with this rho, and as a result, rho will be replaced by mu, so we get the same thing. And therefore, we get delta mu of phi. So thus I've shown that the derivative of this first term just gives me this thing. This might look complicated, but it's not. What we're doing here is simply the generalization that if I have a term like half of phi dot squared, and I take the derivative of that with respect to phi dot, then I just get phi dot. That's exactly what it is. And if I have half of phi prime squared, and I'm taking the derivative with respect to phi dot, sorry, this is a phi prime, then I should get 0. This is all that I'm saying. Okay. So having done this, now we can write what our T mu nu is. So T mu nu is going to be the conserved current is going to be minus delta mu nu, and inside we're just going to have the Lagrangian density. So del mu of phi, so let's call del, say rho, del rho of phi minus half m squared phi squared, and then for the second term we're going to have del mu upstairs of phi, del nu downstairs of phi. So we can now lower the mu index, then we have a rank 2 tensor, and it's going to give me, we can write this term first. So we're going to get del mu downstairs phi, del nu downstairs phi, and then we're going to have minus eta mu nu, because when you lower the index of a delta, that's what you get. So you should know this, delta mu nu, eta mu rho is going to give me eta nu mu. So you should verify that. So, and then we will have times half of del rho phi minus half m squared phi squared. So this object is an important object in physics, and it's called the energy momentum tensor. Okay, and this plays a central role in both quantum field theory as well as general relativity. So, as I said before, the energy momentum tensor is a set of 4 conserved currents, and therefore they're all conserved. And so there are 4 conservation equations, and those equations can be written like this. Now, because there are 4 conserved currents, there'll be 4 conserved charges, and we can label those charges by, say, P nu, and they will be given by the integral of the 0th component of the currents integrated over all space. So these will be the 4 conserved charges. If we now work this out, P0, which we call the Hamiltonian, and this will be given by the integral over all space, let me just call that sigma, of T00 d cubed of x. And so if I work this out, you can see that this becomes phi dot squared minus half of phi dot squared plus the gradient of phi squared plus m squared phi squared integrated over all space. And here you can see that this minus this is going to give you half. This is going to give you half of phi dot squared, which is the kinetic energy of the field. And this is something positive. And this justifies our earlier choice of sign. So this is going to be half times phi dot squared plus grad phi squared plus m squared phi squared. So this also matches our previous expression for the Hamiltonian. We can also derive the 3 momentum. And if you look at the 3 momentum, they will be given by the integral over the T0I. And it's easy to see that this is nothing but minus phi dot, the spatial derivative of phi, and if you use the definition of the canonically conjugate momentum, this becomes pi. This is just pi. And then the spatial derivative of phi. This is the expression for the conserved momentum. So what we have seen is that the conservation of energy and momentum are a result of the symmetry under time and space translation. So let me write that out.